Okay, Chapter 4, Section 3, How Derivatives Affect the Shape of a Graph. In this section, we're going to explore how the first derivative and the second derivative impact the shape of the underlying function. And also, we're going to be working with graphs and then studying the graph to see if we can deduce something about the first derivative or the second derivative. Okay, remember that taking one derivative of a function gives the first order derivative, or the derivative of order 1. Since the derivative is used to find the instantaneous slope of a curve, we use it to characterize several features of functions and models. Okay, so let's begin with the following graph. Say we're working with this equation, 1 minus, and then in parentheses, x minus 3 squared. This online graphing tool finds the graph for us. So it's a parabola, opens upside down. So let's take a closer look at this graph and examine the derivatives associated with it. If we think about the tangent lines as we progress through the graph, they would look like this. So at this point, this line right here represents the tangent line. Right? So as the tangent line goes from there to there, we see the slope of that tangent line. Let's think about that slope of the tangent line. Over here, we have a very large positive slope. Okay? That black line has a very steep positive slope. As we get closer and closer in this direction, we still maintain a positive slope, but it's getting a little smaller. Okay? And then as we get closer and closer and closer to the vertex point here of the parabola, we still have a positive slope, but it's getting smaller and smaller and smaller. Right? Still positive, but smaller and smaller. Still positive, but smaller and smaller and smaller, until we reach a horizontal, at which point the slope is 0. Then we begin with a small negative slope. Then a bigger negative slope, then a bigger negative slope, and then bigger and bigger and bigger and bigger and bigger and bigger and bigger. So there's a very steep negative slope, and they just keep getting bigger and bigger and bigger and bigger in that direction. Okay, so what we're interested in focusing on right now, don't worry about that equation yet. We want to look at the graph. We want to think about the tangents, and we want to think about the slopes of those tangents. In this particular graph, they started off as very big positive slopes, and then smaller positive, smaller positive, smaller positive to 0. Right? There's a flat horizontal. Oops. Right up here, the slope is equal to 0 at the top, and then a small negative, and then a bigger negative, bigger negative, bigger negative, bigger negative, bigger negative, coming all the way down. So the equation of our function was f of x was equal to 1 minus x minus 3 squared. Okay, so don't worry about the equation yet. Right now we want to focus on graphs. I just needed it to create that graph. So we'll start off with graphs. We'll study the graph, see what we can interpret from the graph, and then later we'll focus our attention on the equations and what we can interpret from the equations. Okay, so first of all, this leads to this, right? So this parabola is the graph of f of x. And if we think about the tangent lines at various points, right, so just a few kind of exemplary points, there is a line that has, something there, for example. That's the tangent there. And then another one over here. Here's the tangent there, right? So if we think about the slopes are positive, right? And they're pretty big positives. And then as we get closer and closer and closer, over here, oops, over here, right? The slopes are still positive, but they're getting smaller and smaller and smaller until we reach the top here. And we all know now that when the tangent line is horizontal, the slope is going to be equal to 0. Okay, so let me just do shorthand notation to think about this space here. So we have at 3 there, we have the values that are to the left of 3, over here highlighted in yellow, to the left of 3, And then I'm going to highlight in green the values to the right of that 3. That's this over here. And the distinction there is that right at 3, that derivative is going to be equal to 0, right? So right here, the derivative evaluated at 3 is going to be equal to 0, right? Because the slope is going to be horizontal. The slope is going to be 0 because the tangent line will be horizontal. So if we focus on everything to the left of this 3, what we can say is that everything to the left of 3, everything over here, for all of these values, the derivatives are going to be positive, right? The slopes of the tangent lines are always going to be positive. So we would note that as this, f prime of x in this region over here is greater than 0. It's always positive. Or we can just say f prime of x is positive. Positive. Good. To the right of 3, everything over here, let's think about that. Let's think about all those derivatives. So the tangent lines are going to start off with, say, something here. Here's one point there. And then maybe another one over here. So here's just some examples of where the tangent lines are. And what we notice is that for all of these points over here, the slope of the line's tangent are always going to be negative, right? Negative slopes. So we would say that f prime of x is going to be less than 0, strictly less than 0 in any one of these values. Or we would just say that f prime of x is negative. Negative. Okay? So we have slopes that are a big positive over here. Big positive slope. Positive slope. Notice that there's a distinction between the actual value of my function and the slope of the tangent line. Here, for example, the actual value of the function is a negative, right? It's below the x-axis. This is the x-axis over here. So it's below the x-axis. So this point on the function is negative. However, the slope of the line tangent at that point is a pretty big positive number. Okay, and then as we move forward, we get to like a place like up here, say like this point right there. At that point, at this point, the point on the function is now positive. It has crossed through the x-axis over to the other side. So this point on my original function is positive. And also the slope of the line tangent is also going to be positive, but it's a much smaller positive than it was over here. So I'm just going to say that at this point over here, the slope is a small positive. Small positive. Small positive slope at that point. Then we get to, actually let me clarify, it's at this point here, the tangent line there. It's going to be a small positive. And then right at the top there, we have a horizontal line. So let me point that out. At this point here, we have a horizontal line, horizontal asymptote, horizontal tangent line, which means that the derivative at that point is equal to 0. Now, in this case, I just happen to see that it's right at 3. So f prime of 3 equals to 0 right at the top there. So we have a 0. And then right after it, we see that the tangent lines start to have a negative slope. So at this point right here, what we have is a small negative slope. Small negative slope. Again, don't make the distinction between the value of my function and separate that from the slope of the line tangent. So at this point, the actual function is positive. We're above the x-axis, so we're up here. That's our point. So the value is positive. But the slope of the line tangent at that point is a negative slope, right? Okay, and now if we keep going, we see that the slopes are getting bigger and bigger into the negatives, right? It's a steeper negative slope. So somewhere over here, say at that point right there, we have a big negative slope. Big negative slope. And at this point, the actual value of our function is also negative. That's what we have here. Okay, so what we want to get out of this is that whenever the first derivative is positive, the first derivative is greater than 0, look what's happening to our underlying function. Our underlying function is increasing. Right? It's getting bigger. So when f prime of x is positive, when f prime of x is greater than 0, what I can conclude is that the original function f of x is increasing. Notice that you could be increasing and still be in the negatives, right? So this whole section over here, the function is negative. It's negative this whole way through up until we get to there, but it's increasing and it punches through the x-axis. It keeps increasing all the way up until there. And then at that point, the function begins to decrease. So when the first derivative is less than 0, when the first derivative is negative, what we can conclude from that is that the original function, f of x, is decreasing. And again, don't make the mistake of thinking that decreasing automatically means that the function is negative. It doesn't have to be. This whole portion over here, starting from 3 to the right, this whole portion over here, the function is decreasing. Let me put it in a highlighter. So starting from here to the right, everything to the right coming down this way, everything over here, the function is decreasing. Over here in this direction, on this side, everything in this side, the function is increasing, right? When we're thinking about increasing or decreasing, you should always walk from or look at it from the perspective of, so for example, think of a little stick person walking on this function from left to right, the way we read, always from left to right. Over here, he has a very steep climb. It's a very large positive slope. As he gets closer and closer to this direction, he still has to walk uphill. The slope is still positive, but it's much smaller, right? It's less steep. At the very top, here, the slope is 0. It's a flat horizontal, and then begins to have a small negative slope coming down here. And by the time he gets over here, it's almost free fall, right? It's a very steep negative slope. Okay, so think about that little person walking up and down this graph. When is he going up? That's the part where he's increasing. The slopes are always positive. That's independent of whether the actual graph is in quadrant 1 or 2, or it crosses from 1 into 2, or excuse me, from 4 and 1, crosses from one quadrant to the other. It doesn't matter if the underlying function is positive or negative. The steepness of the graph is what we're looking at. So here's another app that accomplishes the same thing. We have our same equation here, this parabola. Here is the equation, 1 minus x minus 3 to the power of 2. So here's our equation. And then we see that this applet automatically gives us the tangent line. But this one kind of provides for us an idea of what the slope will be by creating this right triangle underneath it. So as I move the point that travels, the point Q travels on our function. So just to focus on the point Q for a second, it travels on the parabola and goes like this. Okay? And so if we think about the slopes, at this point, this tangent line is a very steep positive slope. And as we get closer and closer and closer to the top of this parabola up here, we see that the slope is still positive. It's going to be a smaller and smaller and smaller slope until we get to somewhere around there. It's going to be a very, very small positive slope. Let me zoom in some more. Very small positive slope, small positive slope, small positive slope until we get to 0. And then at that point, we keep going, we have a very small negative slope, bigger negative slope, bigger negative slope, bigger, 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 bigger negative slope, bigger negative slope, all the way until we keep going. Bigger, 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 bigger. Okay, so now if you notice this other little dot that's traveling around there, the nice thing about this applet is that it also keeps track of what that slope would be. So let me zoom out a little bit more. So over here, for instance, I have a big positive slope. So it's actually 6 at this point. So this program calculates it and says that at this point, the slope is 6, a positive slope. And it graphs that point right there. And then as we travel up, we see that the slope is still positive, but it's getting smaller and smaller and smaller and smaller. And that's what this is, right? This blue dot here represents the value of this slope at this point. As we get closer to the top of this guy, we see that the slope is still positive, but much smaller. Zoom into there. Right? The slope is still positive, but a little smaller. And then as we get very, very close to the top, we see that, boom, finally, the slope is 0 at that point. That's why this dot is there. And then as I go just a little bit past that, then I get a very small negative slope. And then a bigger negative slope, bigger negative slope, bigger negative slope, and I see that this dot just kind of continues to travel down. Okay? Okay, so all of that leads us to the increasing/decreasing tests. So, A, if the first derivative is strictly greater than 0 on an interval, then f is increasing on that interval. B, if the first derivative is less than 0 on an interval, then f is decreasing on that interval, right? So this part here, that f is strictly greater than 0, that's just another way of saying that that first derivative is positive. F prime of x is positive, right? That's what that means. So if f prime of x is positive on an interval, then f is increasing on that same interval. Likewise, over here, this f prime of x is strictly less than 0. Again, that's just a nice way of saying that the first derivative is negative. Okay, so if the first derivative is negative on an interval, then f is decreasing on that interval. Okay, so let's do an example. Okay, say we are given this function. F of x is x cubed minus 2x squared minus 3. Part A. Which values of x correspond to horizontal tangent lines? Part B. Which values of x, for which values of x is f of x increasing? For which values of x is f of x decreasing? And finally, sketch a graph of f at any horizontal tangent lines. Okay, so we know that the horizontal tangent lines occur when the first derivative equals to 0. And we just learned that the function is increasing when the first derivative is positive, and that the function is decreasing when the first derivative is negative. All right, let me write that down. So f of x is increasing when f prime of x is greater than 0. It's positive. Right? That means that the function is on its way up, it's increasing. And f of x is decreasing when that first derivative, f of x, is less than 0, whenever it's negative. Okay? All right, so for that reason, we know that in order to be able to answer these questions, we got to figure out that derivative. So let's begin by taking the derivative. F of x is equal to x cubed minus 2x squared minus 3. So f prime of x is equal to d dx of x cubed minus 2x squared minus 3, which means that f prime of x is going to be equal to 3x squared minus 4x plus 0. So here's our derivative. For part A, for which derivatives the horizontal line tangent, for which values of x correspond to horizontal tangent lines, we know that horizontal tangent lines occur horizontal tangent lines occur whenever f prime of x equals to 0. So that's going to be our first order of action here. So number one, we found the derivative, so we got that done. But now, for part A, we're going to find all x such that f prime of x equals 0. So we're going to set 3x squared minus 4x equal to 0 and solve it. This one should be easy. We factor out an x, we get x, and then we get a 3x minus 4 equals 0. So from the zero product property, right, we have two terms here. We have x times this one, x times 3x minus 4 equals to 0. So from the zero product property, we can conclude that either the x is a 0, either the x is 0, or 3x minus 4 equals to 0, which means that 3x equals to 4, or that x equals to 4/3. So for part A, we've established that when x equals to 0, the first derivative of this function is going to be 0. From here, we've established that f prime of 0 equals 0. And from here, we've established that f prime of 4/3 is also going to be equal to 0. Coming back to the underlying function, the underlying function is valid at 0 and at 4 divided by 3. Those 2 points are in the domain of this function, right? The original function, the domain is all real numbers. It's a polynomial. So it goes from negative infinity to positive infinity. And so I know that 0 is in there. 0 is in there. And I also know that 4/3 is in there. So f of x is defined on those 2 points. So x equals to 0 and x equal to 4/3 is in the domain of f of x. Okay, so what that gives us now is going to be a number line like this. Think about the number line. And we have 0 in here. And then we also have 4/3. And the graph is doing something there. I don't know what it's doing yet. You know, maybe the underlying graph, I don't know, maybe it looks like that. I don't know. Or maybe it comes down and does that. I don't know, right? So I don't know what the original function does. But what I want to do is think about what is the derivative doing in these zones. Okay, so I'm going to think about all the numbers in my domain from negative infinity all the way up to 0 there. And then I'm going to think about all the numbers between 0 and all the way over to 4/3. And finally, I'm going to think about all the numbers that are greater than 4/3. I'm going to pick a test point from one of these places, and it doesn't matter which one you pick. You know, all things being equal, why not pick a nice easy one? So 4/3, for example, is a little bit bigger than 1, so 1 is a nice test point. And then to the right of that, 2 is a nice convenient test point over here. I could pick 3 or 7. I could pick 78 if I wanted to, but why make your life more complicated than it needs to be? 2 is a perfectly good choice. And then over in this zone, it's got to be less than 0, so why not -1? -1, right? So these 3 are going to become my test points. And what I want to do is figure out what is the derivative doing at these test points. I don't necessarily even care what the actual value of the first derivative is at those points. All I really care about is whether the first derivative is going to be positive or negative in each one of these three zones. Okay, so for this first one, let's put it over here. So we have f prime of blank equals 2, and so the first derivative is 3 times blank squared minus 4 times blank. And I'm going to plug in that negative 1, negative 1, negative 1, negative 1. And so this will be equal to negative 1 squared is 1, so this will be 3. And then minus 4 times negative 1 is going to become plus 4, so I know it equals to 12. So f prime of negative 1 is 12, but all I really care about is that it's positive. Positive. Okay, so I'm going to come back up here, and I'm going to put pluses right above here, just to indicate that my first derivative, f prime of x, is positives in this little zone here. I know that it's 0 there. Above 0 is 0, so f prime of 0 is a 0. What about this little zone? Okay, so we have a little test case there. So f prime of blank equals to 3 times blank squared minus 4 times blank. And now I'm going to plug in a 1 there, 1 there, 1 there. And so I'm going to get that f prime of 1 is equal to 3 times 1 squared is just going to be 3. And minus 4 times 1, that's going to be minus 4. And so this is going to be equal to negative 1. And again, I don't even really care about the number. I just care that it's negative. Negative. So in this little blue zone over here, I'm going to say that that first derivative is negative. Okay? This whole line above here is referring to the derivative of our function, not the original underlying function. So again, don't confuse this to mean that this means that the original function is below the x-axis. That's not what it means. It means that the first derivative is negative. It means that the underlying function is going to be decreasing in this zone. Okay. Finally, let's do the last test point. F prime of blank equals to blank times blank, 3 times blank squared, minus 4 times blank. And so now we're going to put in a 2 in here. So put a 2 in there, 2 in there, and 2 in there. So f prime of 2 is equal to 3 times 4, which will make it 12, minus 8. So f prime of 2 will be equal to positive 4. And again, all I really care about is that it's positive there. It's a positive number. So f prime of 4/3 is 0. So we're going to get a 0 there at 4/3. And then it's going to be positive values to the right of that, right? We keep going this way, they're going to be positives, right? Again, just to highlight, this right here means that f prime of 0 equals to 0. And this one means that f prime of 4/3 equals to 0. And then in this zone right in here, in this zone, we're saying that f prime of x is going to be greater than 0. It's positive numbers. We did it by confirming it with 1, and I'm not proving it to you, but take my word for it. The rest of these are all going to be positive, right? If you pick one, whatever you get there, whether it's positive or negative, it'll always be there. We'll confirm this with a graph in a minute. Okay, in this little zone in here, we've established by using a test point that the first derivative is negative. It's less than 0 there. And finally, over here, we've established that that first derivative is greater than 0. Okay, and so now what we can conclude is that the underlying function in this zone, f of x, right? Notice the distinction. This is not f prime of x, not the derivative. This is the original function, f of x, must be increasing. Is increasing in this zone here. Let me extend this out. the original function f of x is decreasing in this zone because that first derivative is negative. And finally, in this last zone over here, f of x is increasing. Okay, so we have a lot of information about our underlying graph f of x. We know it's increasing in this zone. We know that it's decreasing in this zone. And we know that it's increasing in this zone. We can be more specific about where it's increasing by putting the interval. So f of x is increasing from negative infinity up through 0, and then it equals to 0 at 0. And then f of x is decreasing from 0, starting at 0, through 4/3. From 0 to 4/3, the function is decreasing. And f of x is increasing from 4/3 to infinity. Good. So we have all that information there. Let's come back up here and look at our original function and figure out a few other interesting points. So if we take f of x now and factor it, f of x equals to x cubed minus 2x squared minus 3. Well, it's not easy to factor, is it? But we can easily find, for example, f of 0. F of 0 will be the case when x equals to 0. X equals to 0 will be a point where our graph is going to cross the y-axis. So this will be equal to 0 cubed minus 2 times 0 squared minus 3. So we get f of 0 equals to -3. Okay, so we have the y-axis, y-intercept point. And to find the x-intercept points, we'd have to set this equal to 0 and factor, which isn't going to be very pretty. So let's not worry about that right now. And let's take a look at the graph and confirm that the things we discovered make sense. Okay, so I'm going to come over to Desmos and graph this guy and then confirm that the information we have here fits our graph. So using this graphing tool, here's our equation, x cubed minus 2x squared minus 3. And this is what the graph looks like. And let's confirm what we have. Let's take a look at the derivatives. Okay, so starting here, we can see that over here, the derivative is going to be a large positive number. Derivatives are positive. The actual value of the function is negative. The underlying function is negative at this point q here, but the slope is positive. It's a big positive slope. And as we get closer and closer and closer and closer to the y-intercept point here at 0, -3, which we found, we see that the slope is still positive, but getting smaller and smaller and smaller and smaller until we get to there. And then we have a tangent line. So there's one of our answers for part A. We know we have a horizontal line at this point right here, which is the point 0, -3. When x equals to 0, the horizontal line is, the tangent line is horizontal, which means the slope is 0. Following just a little bit past that, we see that the slope is going to turn into a very small negative. Zoom into there a little bit more. The slope is going to be a small negative, and then it gets to a bigger negative, bigger negative, bigger negative, bigger negative. Right? It's negative all the way out through here. And it's going to go all the way out until we get to the point down here. Right down there. At which point we have another horizontal. Let me zoom into there. At which point we have another horizontal there. This is going to correspond to the x input value of 4/3. Just a little bit past 1. It's going to be somewhere over here, a little bit past 1. So again, focusing on the slope was a big positive, smaller positive, smaller positive. At the very top here, we have a zero, and then it changes to a small negative, bigger negative, bigger negative, bigger negative, negatives, 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 and then it starts changing to a smaller negative, but still negative, 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 all the way until we get back to zero slope, and then a small positive slope, bigger positive slope, bigger positive slope, bigger positive slope, going on forever. Okay, so that matches with what we figured out from just the equation, right? The graph matches that. Okay, so here's the exact same graph using Desmos. I like Desmos for certain reasons. I like the other one for certain reasons. But anyway, so it's the exact same graph. As we see, I just kind of changed the scaling it a little bit. And again, we could see that as we have a derivative go through it, let's say we have this point here at A, we're going to start off with a very large positive slope over here. Any tangent line at this point is going to have a large positive slope. And then it gets a smaller positive slope until we get to zero. And then a small negative slope, bigger negative slope, bigger negative slope. At some point, we're going to reach the biggest negative slope at somewhere around there. And then it becomes a smaller negative, smaller negative, smaller negative slope until we get back to zero. And then we cross zero, become a small positive slope, bigger positive slope, bigger positive slope, until it just keeps going on. Okay, so matching it up to the work we had before, we know that we had a y-intercept point here at 0, -3. And we know that another interesting point is this point here at 4/3. So I know that that translated to a point here. To a point here, which is 4/3, x equals to 4/3. And then this, of course, translates to x equals to 0 right in here, that point there. Earlier, when we were working with our equation, right, our equation was f of x equals to x cubed minus 2x squared minus 3. And then we also found the derivative f prime of x was equal to 3x squared minus 4x. So working with this is how we found these 2 points. And so now what we want to highlight here on the graph is to point out that we figured out that on the interval from -infinity to 0, we know that the derivative is going to be positive. F prime of x is always positive, right? If you think about these tangent lines over here, the slopes, the tangent lines at various places here, the slopes are always positive. Sometimes they're big positives, sometimes they're small positives, but they're always positives. So f prime of x is positive in this interval from -infinity to 0. We also know that, as a consequence, that the original function is increasing. Right? As we can see, the function is on its way up. Notice that in this particular case, the function is always negative, but it's increasing. Good? So the derivative is positive. The underlying function happens to be negative here. But the function f of x is increasing on this interval. Okay, on the interval between 0 and 4/3, if we think about the derivatives that exist in this little interval, they're always going to have negative slopes. So we have a tangent line there, a tangent line there, a tangent line there. All these tangents at all these places are all going to be negative. So we would conclude that on the interval between 0 and 4/3, f prime of x is less than 0. It's negative in that interval. And so we can conclude that the underlying function f of x is decreasing. Okay. It's decreasing, and it also happens in this case to be negative. So negative and decreasing in this zone. Good. And then the final section over here, starting from this point on that way, the function is the slopes of the line's tangent are all going to be positives. So here we have some positive slope on the tangent line, and then another positive slope, and then another positive slope, right? The slopes are all going to be positive. Sometimes a small positive, sometimes a really big positive, but they're all positive on that interval. So from the interval from 4/3 to infinity, positive infinity, we can confirm that the first derivative is going to be greater than 0. Sometimes a small positive, sometimes a really big positive, but always positive. And so the underlying function f of x is increasing. Good. And that matches up with the work we just had a little bit ago. Okay. And then finally, we were asked to identify places where the horizontal line, so the tangent line is horizontal. And so we can see from our graph that it's got to be here and here at these 2 points. Let's put it in green. There are horizontal lines there and here. Right? Tangent lines are horizontal. Okay, so if you're thinking about how does this relate to your homework, so sometimes you'll just be given a graph to begin with, no equation at all, just a graph, and you might be asked to establish from the graph when is the first derivative going to be positive, right? We can see that that's going to be wherever the function is increasing. You might be asked to interpret from the graph when is the first derivative going to be negative. Again, from the graph, we can see that it's going to be wherever the function is decreasing. Notice that we have a little bump here, and that occurs when the tangent line is horizontal. That occurs when that first derivative is 0. And it's also important to note that we found it by finding that the first derivative, whenever the first derivative is equal to 0, but then we also had to come back and double check, make sure that that value is in the domain of our function and nothing weird is happening at that point. Okay, all right, move on. Okay, so critical numbers. A real number x in the domain of f such that f prime of x equals to 0 or f prime of x does not exist is called a critical number of f. Okay, so the critical numbers of f that are in the domain of f are partition numbers for f prime. So the partition numbers for f prime are the values that make this true. The first derivative at that point is equal to 0, or the first derivative at that point does not exist. Those are the partition numbers. When we are working with an equation, we're going to be given some function f of x, right? So we'll be given in our homework some function f of x. So then we find the derivative f prime of x. We're going to set this equal to 0, find all values such that this equals to 0. Here, let me find all x such that either f prime of x equals to 0 or f prime of x equals to does not exist. Right, so we find all those x values. Those are the partition numbers. Whatever those values are, those are the partition numbers. Now, after we find all of them, right? I didn't give you an equation here, but let's just say, just for the sake of having something, we find that x equals to, or f just for the sake of having something in this example, let's say that we find through a lot of work that f prime of 3 equals to 0, and we also find that f prime of 4 does not exist. And let's find one more. Let's say f prime of positive or negative 1 is equal to 0. Okay, so then we'd say that x equals to 3, -1, and 4 are partitioned numbers. Are these partition numbers? Good. Now we come back and we check at the domain of f of x. Maybe it turns out that the domain, domain of f of x, maybe it's just all positive numbers. Got to go from 0 to infinity. So that would mean that this -1 is not in the domain. So if it's not in the domain, that means that this partition number is not going to qualify as a critical number. Okay, so then in this little made-up example, it would mean that x equals to 3 and x equals to 4 are what we call these critical numbers. Critical numbers. Critical numbers are a real number x in the domain of f such that its derivative is 0 or its derivative evaluated at that point does not exist are called the critical numbers. Okay. When we're dealing with a polynomial, polynomials are really nice. There's no weird vertical asymptotes anywhere. There's no breaks. They're continuous. So if we're dealing with a polynomial, then both the partition numbers for f prime and the critical numbers of f are the solutions of f prime x equals to 0. Okay. Why is that? Remember, the domain of a polynomial is all real numbers. Right? So there's never going to be a case where you find a partition number and it's not in the domain of f. That's not it. That's not the case because for a polynomial, the domain is all real numbers. And also, when you're working with a polynomial, you're not going to find a case where the derivative doesn't exist somewhere. Remember, polynomials are differentiable on all real numbers as well. Okay, so in the case of polynomials, we'll have a really nice situation where the critical numbers are the partition numbers, and they all result out of this, that the first derivative of x equals to 0. Okay, so find the critical numbers of f, the intervals on which f is increasing, and those on which f is decreasing for this function. F of x equals to the 5th root of 2 minus x. Okay, so let's begin by rewriting this. So let's rewrite it as f of x equals to 2 minus x to the power of 1/5. And then we know that we need to work with the derivative, so let's find the derivative of this function. Back to x of this function. So we know we have to use our chain rule. So f prime of x is going to be equal to 1/5 times 2 minus x to the power of 1/5 minus 1 times the derivative with respect to x of 2 minus x. So this is going to be 1/5 2 minus x to the power of -4/5. Common denominator there for the 1. Times, and then the derivative of this function is just going to be a -1. So we can simplify the whole thing a little bit by saying that the first derivative is going to be equal to a giant fraction where the only one that's in the numerator is this -1, and in the denominator we'll have this 5 times 2 minus x to the power of +4/5. Okay, so step 1, find the derivative. When you're doing your homework, not really sure what to do, just start there. Find the derivative. Found the derivative. Okay, now step 2 is we need to figure out all the values of x such that, right, find all, we'll stick to x, find all x such that f prime of x equals to 0, or f prime of x equals to does not exist. All those values will be partition values. And then once we find those values, we'll confirm that those values are in the domain of the original function. And if they are, they'll be upgraded to become critical values, right? And that's what they ask for. Find all the critical values of f. Okay, so when will this derivative equal 0? Well, note that, so for this one, when they equal to 0, note that 2 minus x raised to the power of 4/5 is the same thing as 2 minus x raised to the power of 4, and then that whole thing inside the 5th root. Right? Those two things mean the same. And then if we take any number, positive or negative, and then we raise it to the power of 4, we're going to get a positive number. So for any x, 2 minus x to the 4th power will be some positive number, or it could be 0. It could be greater than or equal to 0. Let me write it that way. Will be greater than or equal to 0. Obviously, if we let x equals to 2, that's an easy one. That'll be the 0. But otherwise, it doesn't matter what you choose for x. You're going to end up with a positive number. And then if we take the 5th root of a positive number, we're going to get a positive number. So the point is here that this is always strictly greater than or equal to 0. Okay? There's no way that we're ever going to be, we'll be able to get a negative. So 2 minus x to the power of 4/5 is never negative. Okay, so if the denominator is never negative and the numerator is -1, that means that f prime of x is a negative number for almost all values, right? The only possible exception is when the denominator is 0. Okay, so f prime of x is always going to be negative, for any input value of x except when x equals to 2, right? If we just ignore that for a second, any other input value, well, we're always going to get a negative. Point being is that it's never going to be 0. So there's no way that this will ever happen. The derivative is never 0. Okay? Well, what about this one? Well, we just established that when x equals to 2, we'll get a 0 in the denominator. And so therefore, we'll have a fraction where the denominator is 0. And that's where we'll have a does not exist. Okay, so let me zoom out of here. Note that f prime of 2 is equal to -1 all over 5 times 2 minus, let me put a blank here, to the 4/5 power. So if we put a 2 there and a 2 there, we'll end up with something that has -1 divided by 0. That's a does not exist. Okay, so at this point, we've established that positive 2 is a partition point. So x equals to 2 is a partition point. Okay, and now we come back and we think about our underlying function, the original function, and think about the domain. So f of x equals to the 5th root of 2 minus x. We just have to make sure that, well, because this is a 5th root, it's not an even root. I could have negatives inside. That's okay. There's nothing wrong with taking the 5th root of a -7. I can also have a 0. I can have anything I want. So the domain is going to be all real numbers. Domain is from -infinity to +infinity, all real numbers. And so certainly 2 is in there. X equals to 2 is in the domain. So now I can upgrade that point to not be a partition. Now it's a critical number. And it's the only one. So x equals to 2 is the only critical number. Okay. There will be cases where we find a partition point and then we come back and think about the domain and it might not be in there. And if it's not in there, then it's not a critical point. So there are values that can be partition points, but then they don't qualify, they don't upgrade to become a critical point, a critical number. Okay, so we found the first part, find the critical numbers of f. The next part says the intervals on which f is increasing or decreasing. Okay, so we've established over here that f prime of x is always negative for any input value, always negative. So if it's always negative, that means that the function is always decreasing, right? The first derivative is negative, means that the underlying function is decreasing. So f prime of x is always negative on the interval from negative infinity to 2 union 2 to positive infinity. So this covers every single possible input value except 2. And we know that the function is continuous at 2. So remember, the derivative is not defined there. However, the function is defined there. It's 0. Right? So at x equals to 2, f prime of 2 does not exist. However, f of 2 does exist. That's just going to be equal to 0. It's the fifth root of 2 minus 2, which equals 0. Okay. So f prime of x is always negative on these two intervals. And then at x equals to 2, it is continuous at that point. The underlying function is defined at x equals to 2. The derivative is not defined, but the underlying function f is defined at 2. It's continuous at 2. So we can conclude that the function is always negative. So f of x is f of x is always decreasing. Is always decreasing, or is decreasing on all real numbers from negative infinity to positive infinity. Always decreasing. Okay, let's take a look at a graph, see what it looks like. Okay, so this is what the graph looks like using this little applet guy. Right, so I just typed it in. 2 minus x to the power of 1/5 looks like this. And then let's think about the tangent lines, the slope of the tangent lines. Do you see how they're always going to be negative? Except here. So at 2, we end up with a vertical asymptote. And we know that the slope of the line that's vertical is undefined. Right, so let's bring in this guy here. So as we come forward this way, we see that the slopes are always negatives. Negative slopes, negative slopes. In fact, let me zoom into here. So we have a negative slope, and then we end up with like bigger negative slopes. They're always negative, right? Little stick person walking from left to right is always going to be going downhill. The slope is always negative. And then it gets to a steeper negative, steeper negative, steeper negative, steeper negative, really steep negative, hugely steep negative. It's a huge, and then at that point, it's a vertical line, which means the slope is undefined, right? The slope of a vertical line is undefined. And then as we keep going a little bit past that, we still end up with a negative slope. It's let me zoom in a little more over here. A little bit past the 2, we end up with that. It's a really big negative slope. And then slightly smaller, but still pretty big negative slopes. Negative slopes, negative slopes. So coming on through. Negative, 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 negative. Okay, so from left to right, starting all over again. A little stick person here would be walking downhill, right? The slopes are negative. Always negative slopes, always negative slopes. Tangent lines, the tangent line always has a negative slope. And then bigger negatives, bigger negatives, bigger negatives, still negative slopes, then undefined. And then a little bit past that, all of a sudden we have negative, 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 negative. Okay, so this graph hopefully confirms that this function is has a negative slope everywhere, and the derivative is undefined at 2, but the original function is not undefined at 2. At 2, the answer is 0. So it's continuous at 2. So we can just conclude that this entire function is going to be decreasing for all real numbers, right? The first derivative is always going to be negative everywhere except here, which is where it's undefined, just at one point. And so we can bring that together to conclude that the underlying function is always decreasing on all real numbers. Okay, one more example. Find the critical numbers of f, the intervals on which f is increasing and those on which f is decreasing for this function. F of x equals to 1 over x plus 3. So again, we know that we're going to have to find the derivative, so I'm going to just jump right ahead and rewrite this as x plus 3 through the power of negative 1. And now I want to find the derivative. So f prime of x is going to be equal to negative 1 times x plus 3 to the power of negative 2 times the derivative of the inside part, d dx, using our chain rule, x plus 3, which is just going to be equal to 1. It's just going to be equal to 1. So this is an easy derivative. It's going to be f prime of x is equal to negative 1 all over x plus 3 squared in the denominator. So we found our derivative. That's step 1. Next, we want to find all the values of x such that the derivative equals to 0 or is undefined. Similar to the example before, so find all x such that f prime of x equals to 0 or f prime of x does not exist. That's what we want to look for. There's going to be no solutions for this one. Similar to the example we just went through, note that the denominator is always going to be positive or 0. So note x plus 3 squared is always greater than or equal to 0. No way this could ever be negative. And the numerator is always negative 1. So there is no value, there's no way for this to be equal to 0. Okay, so there's no solutions to this one. What about this one? Well, the case when x equals to negative 3 will cause an undefined. So note that x plus 3 squared, if we set that equal to 0, we find that x equals to negative 3 will be our value, our solution to that. So x prime of negative 3 will give me negative 1 over 0, which means that it's undefined. So this is the case of does not exist. So at this point, we found that x equals to negative 3 is a partition point. Partition point. It's a value of x such that one of these two things is true. Well, in this case, it was the does not exist part. Now we want to see if this can be upgraded to a critical number, right? In order to do that, we got to come back to the original function and see if negative 3 is in the domain. So note that if we come back to f of x equals to 1 over x plus 3, the domain is all real numbers except negative 3. Domain is all real numbers except x equals to negative 3. We can't put a negative 3. If we put a negative 3, we'll end up with a 0 in the denominator, so it's undefined there. And that's exactly the point that I wanted to check to see if it was in domain. It's not there, so x equals to negative 3 is not a critical number. Right? In fact, this particular function has no critical numbers. None of them qualified. Thus, f of x has no critical numbers. Okay, nevertheless, we did find a partition number. So as a partition number, what we're going to do is think about our number line, and then we're going to partition it at -3, and think about the derivative, whether the derivative is positive or negative on either side of it. We know that at -3 it's undefined, but what happens to the left and to the right of that partition number? So I'm going to come back up here. I'm going to put this number line there. I have the number -3 there. And I want to think about the derivative, f prime of x. What's happening to the left of this -3? What's happening to the right of this -3? I already know that at -3, right at -3, f prime of -3 does not exist. Your book puts a DE here, does not exist. Okay, so what do we do here? Well, we can just kind of analyze it and realize what the answer is going to be, or you can take a test point. That's fine too. You can pick, say, -4. We can pick -4, for example. And over here, well, why not pick a nice convenient value? Could be -1, -2. How about 0? 0 is a nice convenient value. And we plug them into our derivative as a test value. And remember, all we really care about is whether the derivative is going to be positive or negative. Now, the other thing we can do is just kind of analyze our derivative here, as we did earlier, and notice that no matter what value of x I choose, the denominator will always be positive because I'm squaring it. So if I'm thinking about my derivative, -1 over x plus 3 squared, the denominator part of this is always going to be greater than or equal to 0. Let's ignore the -3. At -3, it's going to be undefined. But for all other numbers except -3, this is always going to be positive. And while the numerator is just a constant, it's just negative. So I'm always going to have a negative divided by some positive. So the whole thing will always be negative. The first derivative will be negative there. The first derivative will be negative there. And it's undefined at -3. So here again, we have a case where the derivative is negative. So let me write down our conclusions then. So we have that f prime of x is negative on the interval from -infinity up through -3, close, unioned with -3 all the way out to positive infinity, right? At -3, it's undefined, so we wouldn't say it's negative. We'd say it's undefined there. But the first derivative is negative on this interval, so then we know that the underlying function f of x must be decreasing, is decreasing on the same interval from -infinity to -3, unioned with -3 to positive infinity. Good? So there's only one point where the function is not decreasing. The derivative is undefined there. And if we come back and think about the original function is also undefined at -3. So we cannot glue it together like we did before and conclude that it's decreasing on all real numbers. We can't do that. We have to stop here and say that these two are the intervals where our function is decreasing. Right, so this is our answer. Good. And this is a standard function, so you might remember what the graph looks like. So just kind of like a rough sketch of the graph. Just as a rough sketch of the graph, we know that it's going to look something like this. Here is x, here is y. Our graph is going to have a vertical asymptote our graph is going to have a vertical asymptote at x equals to -3. And then the graph is going to come up like this way and this way. Not a very pretty graph, but gets the job done. Vertical asymptote at -3. And we see that if we think about the tangent lines, the slopes are always going to be negative, right? If you think about a tiny little stick man walking on this graph, from left to right, the way we read, he's always going downhill. The slopes of the tangent lines are always negative. They start off as a small negative, then bigger negative, bigger negative, bigger negative, sort of an infinitely bigger negative coming this way, and then they disappear because they become undefined. And then over here, it appears again, and again, the little stick person still walking downhill from left to right. So all the tangent lines are always going to have negative slopes. Tangent lines are always going to have negative slopes. So therefore, the function is decreasing from -infinity to -3. So on this interval from there to there, from -infinity to -3, we can see that our function is decreasing. And again, on this interval from -3 to +infinity, the function is decreasing. Okay, let's graph it using one of our technologies to get a better picture than that. So here I graphed f of x equals to 1 over x plus 3. And let's just jump from over here. So let's zoom in, zoom in. Well, zooming out, you can see a better idea of what the graph looks like. But let me zoom in, zoom in, zoom in, zoom in, like this. And then we can see that the slope is always negative. Right? A little stick person walking here from left to right would always be walking downhill. The slopes are small negative slopes, bigger negative slopes, bigger negative slopes, huge negative slopes, big negative slopes, until we get to this vertical asymptote where it's undefined, and then all of a sudden it jumps to the other side, where we have a really big negative slope, and then smaller negatives, smaller negatives, smaller negatives, smaller negatives, and so on and so forth. But they're always going to be negative slopes, except for the place where they're undefined. So our underlying function is decreasing there and also decreasing there. All right, hopefully that made sense. Okay, next let's take a look at this function f of x here. Don't worry about what the actual equation is, just looking at the graph. And let's think about when the function is increasing, decreasing, therefore we're thinking of the slopes of the lines that are tangent. So coming through here, we see that over here we'd have a tangent line that kind of looks like that. It's going to be a big negative, right? That the slope of this tangent line is going to be a large negative. And then over here, maybe there, it's going to be still negative, maybe a little smaller. Coming closer to here, we'd have smaller, but still negative. And then here we have a 0 for the slope of the tangent line. And then back to being negatives, small negative, and then a bigger negative over here, and then negative, bigger negative, and then a smaller negative, and then 0 again. And then now we have a small positive, right? The slope of the tangent line is small positive, then a bigger positive, then a bigger positive, and then a bigger positive, and then a smaller positive, and then 0, and then a small negative over here, then a bigger negative, and then a bigger negative, and then a really big negative, and then it kind of goes off in toward becoming an infinitely large negative until it becomes undefined, right? The slope is undefined. The tangent line is undefined at this sharp point right there. And then to the right of it, okay, now we're going to all of a sudden become a positive slope. Bigger positive slopes, bigger positive slopes, bigger positive slopes, smaller positive slopes until we get to 0. And then again, a small positive, and then a bigger positive, bigger positive, bigger positive, until we get to this sort of undefined slope again. So the tangent line is undefined at that point. And then all of a sudden we go to negative. The slope of the line is negative. The slope of the line tangent is negative. until we get to this point here, so becoming negative, 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 and then again, negative, negative, negative. Okay, so if we think about just the slopes of the tangent lines, we want to think then about the derivatives, the first derivatives. And we have different intervals here. So I'm going to go through section by section and think about the slopes of the line's tangent or the value of the first derivative. So on this section, from here to here, and then I'll just kind of alternate colors. And then we'll go from here to there, and here to there, and here to there, and here to there. Okay, so in this interval, the derivative f prime of x is going to be negative. Here, at this point, f prime of c sub 1 is clearly 0. Right? It's a horizontal line. On this interval, f prime of x is still negative. Right? The slopes of the line's tangent are negative. Right at c sub 2, we're also going to have that f prime of c sub 2 is going to be 0. We have a horizontal line there. On this interval, then the derivative f prime of x is going to be positive, greater than 0. Then here, again, we have, Here, at this point, again, we have that f prime of c sub 3 is equal to 0. We have a horizontal line. On this interval, from c sub 3 to c sub 4, we have that f prime of x is going to be negative. So the underlying function is decreasing. And then at this point, we have that f prime of c sub 4 does not exist, undefined. Then the function is going to have the slopes of the derivatives are going to be positive in this interval. So f prime of x is positive in this interval. Then we have at this point there that f prime of c sub 5 is again 0. We have a horizontal line. At this point, again, we have that f prime of c sub 6 equals does not exist. The derivative doesn't exist, right? The underlying function is defined there. It's a sharp point at that point, at that value, but the tangent line does not exist. And so in this interval here, we'd say that f prime of x is still greater than 0. It's increasing. The underlying function is increasing. And then on this interval, it's going to be that f prime of x is negatives, less than 0, reaching to that point right there. And then again, f prime of c sub 7, we end up with this sharp point there. So it does not exist at that point. Right? At this point right there, we end up to a sharp corner. And then for the last interval here, we have that f prime of x is negative as well here. Good. So wherever the derivative is negative, so we'll say we can conclude then that on this interval from here all the way out to here, the underlying function f of x is decreasing on this entire interval, and we throw in the value of c sub 1 because it's continuous at that point. Okay, and now from here up to here, from c sub 2 up to c sub 3, the derivative is positive, so the underlying function is increasing. F of x is increasing. Good. Now from here to here, there to there, okay, on that interval from there to there, f of x is decreasing. Decreasing, the original function is coming down, right? It's decreasing, comes to a point where that point is a valid point in our domain, but its derivative is undefined, right? So there's a distinction there, don't confuse it. The derivative is undefined, but the actual underlying function does have a valid point there. It comes to a sharp corner, and we know that the derivative at a sharp corner does not exist. Okay, but now moving forward from here all the way up until here, this whole section, the derivative is going to be positive. So that means that f of x is increasing. We throw in the value of c sub 5 because it's 0 there. So the function is increasing all the way up to there. And then it's decreasing from there to there, and then decreasing again. It's undefined there, but the original function is defined, so that means that on this entire remaining segment, f of x is decreasing. Okay, so what we want to get out of this is the following. When the graph of a continuous function changes from rising to falling, a high point or a local maximum occurs. When the graph changes from falling to rising, a low point or a local minimum occurs. So the first place where that occurs on this graph is here. Notice that the graph is decreasing, decreasing. The original function f of x is decreasing, decreasing, hits 0, and now it's increasing, increasing. So it goes from falling to 0 and then to rising, which means that the derivative had negative derivatives, negative derivatives, negative derivatives, 0, and then positive derivatives, positive derivatives. When we see that occur, we end up with something we call a local max. A local minimum. Good. So this is a local minimum here. And then here we have a case where the function is increasing, increasing, increasing. We get to a 0, and then it begins to decrease, 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 decrease. So if we think about that first derivative, it changes from a positive slope, right, a positive derivative, to 0 to a negative derivative. And at that point, we have a local max. Okay, so this one is a local max, and this one right here is a local min. Okay, so remember that we experienced the change at this point. Over here, we had that f prime of x had negatives, and then over here, f prime of x is positive, which means that the underlying function was decreasing. F of x was decreasing, and then it changed from decreasing to f of x is now increasing. So when that change occurs, we have a possible place where we have a local minimum. We just have to confirm that that value is in the domain of our function. Good. Okay, and then the opposite thing happens over here. Here we have a function increasing, so that means that the derivative is positive. And then next we run into a zone right next to it. It changes to a place where the first derivative is now decreasing. The first derivative is less than 0, which means that f of x is decreasing. And so at that point we have a candidate for a possible local max. We just have to confirm that that value is a value in our function, which it is. You can see here, it's a continuous function, so that's a local max. Same thing happens here. We change from decreasing, the function is decreasing, and then all of a sudden we see that the function f of x, f prime of x is now greater than 0, f of x is increasing. So we've changed from the first derivative is negative to the first derivative is positive. We've changed from the function is decreasing to the function is increasing. That point right there is a value in our function, therefore that's a local min. So local min right there. Now this point here, notice that the function is increasing here up to there, but then it's also increasing on this zone. So f of x is, f prime of x is also increasing in this part right there. So this is not going to be a local max or a local min because there was no change. The function was increasing on the left of that point, and then the function was still increasing to the right of that point. So there is no local max or min at that point. There is a local maximum here. So this one does qualify as a local max. And again, if we think about the slope of the line's tangent, the slopes in this little zone, f prime of x, are going to be negative. So the function is decreasing here, the function is increasing there, therefore that point right there is a local max. This point, again, fails to be local max or local min. So no local max or min at this point. Like this one over here. No local max or min at that point either. Notice that the function is decreasing in this interval, then we get to that point, and then it's also decreasing. There was no change. F prime of x is still negative. So the local maximums and local minimums are going to occur where there is a change in the first derivative from going from negative first derivatives to positive first derivatives, or the other way around, and the order makes a difference in order to figure out whether it's a local maximum or local minimum. Okay, so all of that leads to the first derivative test. Suppose that c is a critical number of a continuous function f. A, if f prime, so the first derivative, changes from positive to negative at c, then f has a local maximum at c. B, if f prime changes from negative to positive at c, then f has a local minimum at c. And finally, if f prime is positive to the left of and the right of c, or negative to the left of and the right of c, then f has no local maximum or minimum at c. Okay, remember that when we are told that c is a critical number, it means that f prime of c, let me write that down. So from the fact that we know that's given that c is a critical number, it means that either f prime of c equals to 0 or f prime of c equals to does not exist. So, and c is a member of the domain of f of x, meaning that f of c is equal to a valid result, valid output, right? Both of those things are true when we are told that c is in the domain of f. Okay, and also remember that this little f prime notation, f prime, is the same thing as f prime of x, right? It's the first derivative. Okay, so as we saw earlier, if we examine the sign of the first derivative and we observe that it changes from positive to negative or the other way around, then we know that we have a local maximum or a local minimum. And if we observe that there is no change, the sign of the first derivative stays positive to both the left and the right of a value c, or the first derivative stays negative to both the left and the right of a value c, then there is no local maximum or minimum at c. Okay, so now we can put everything we've learned together into this sort of all-inclusive table here that's provided in your book. So the first derivative test for local extrema. Let c be a critical number of f, right? If c is a critical number of f, remember then that must mean that f of c is defined, and either f prime of c equals to 0 or f prime of c does not exist, right? We take the derivative, we figure out all the places where the derivative equals to 0 or the places where the derivative is undefined, and now we take those values and we come back and confirm that they are in the domain of f. The values that are in the domain of f are then upgraded to become critical numbers. Okay, so now we take a sign chart, we identify all the critical numbers on our sign chart, and then we either examine our function or maybe take some test points so that we can figure out what is happening with the derivative in those regions. So, for example, if c is a critical point, a critical number, and then we take a test point to the left, and evaluate our first derivative, and it turns out that it's negative there, and then we take a test point to the right and figure out that the first derivative is positive there, then we know that the underlying function is decreasing in this zone because that first derivative is negative, and that the underlying function is increasing in this zone because the first derivative is positive. And now we see a change in the sign of the first derivative. It was negative, and then it transitioned over to being positive, and we know that the value f of c exists. It's defined. So what we have here is that f of c is a local minimum, right? F of c is a local minimum because the slopes of the line tangent change from having negative slopes to having positive slopes. Good. So that's a local minimum. If f prime changes from negative to positive at c, then f of c is a local minimum. On the other hand, we have the same situation, same criteria. We have a c value, which is a critical point, which means it's defined. Then we take a test point to the left of that value. We evaluate our first derivative. We get positive first derivatives. We take a test point to the right of that c value. We evaluate our first derivative. We get negative first derivatives. Then we can conclude that the underlying function is increasing on this interval because the first derivative is positive. We can conclude that the underlying function f of x is decreasing on this interval because the underlying function is, because the derivative is negative on that interval. And because f of c is defined, we see that we have a local maximum at c, right? So that's because we saw a change in the sign of the first derivative. It went from positive to negative, right? So the order matters in order to figure these out. So if f prime of x, so the derivative, changes from being positive to negative, from left to right, the way we read, then f of c is a local maximum. Okay, so if you think about the slopes, they went from positive slopes to negative slopes. So here we have something that looks like this. We have a function that looks like that. And if we think about all the tangent lines, they're going to go from, at C here, they're going to go from having negative slopes to having positive slopes. Therefore, we have a local minimum there. For this one, we have a case where maybe it looks like this. And so here is C. The tangent lines are going to go from having positive slopes to 0 to negative slopes. So that would cover something that looks like this, and we have a local maximum. On the other hand, if we have a critical value c, and then we take test points from either side, and we see that the sign stays the same, either it's positive on the left of c, the first derivative is positive on the left of c, the first derivative is positive on the right of c, or the same, likewise, they're both negatives. Maybe you evaluate the first derivative to the left of c, and we see that the sign is negative. We evaluate the first derivative to the right of c, we take a test point, and we see that the sign is also negative. Then there is no change. In a case like this, it means that the underlying function is increasing all the way through. And in this case, we see a situation where the function is decreasing all the way through. So it might be something that looks like this. Here is a case where it's increasing all the way through, and yet there is no maximum or minimum. Or finally, we might have a case that looks like this. Here, the function is decreasing all the way through, but there is no maximum and there is no minimum. So if f prime of x does not change signs at c, then f of x is neither a local maximum nor a local minimum. Right? And it's the same conclusion here, whether they're positive all the way through or negative all the way through. Okay, let's take a look at some better examples than this. Okay, so here's a nice little table that shows all the various examples we might run into. So again, let's say we have a given function, f of x. In every one of these examples, that's the blue, that's the f of x. In every one of these examples, c is the critical value, therefore c is defined. In this first example, we have a case where to the left of c, the first derivative is negative. To the right of c, the first derivative is positive. At c, the first derivative is 0. And so what we have here is a case where we have a local minimum. Okay, that's what a local minimum is defined to be, a case where we see a transition from a first derivative that's negative to a first derivative that's positive. Okay, here we have a case where f prime of c equals to 0. So we have a horizontal tangent line. Well, by the way, all of these have horizontal tangent lines. Okay, and now if we take a test point to the left of c, the first derivative is positive. If we take a test point to the right of c, the first derivative is negative. And so we see a transition from that first derivative being positive to 0 to negative. When we see this transition, it defines a local maximum. Okay, so at c, we have a local maximum. Good. In this case, we have a case where f prime of c equals to 0. So we have a horizontal tangent line. And then if we take a test point to the left of c, we find that the first derivative is positive. If we take a test point to the right of c, we find that the first derivative is also positive. And so what we have here is a case where the function is increasing on the entire interval. So therefore, f of c is neither a local maximum or a local minimum. Okay, next we have this case where f prime of c equals to 0. So we have a horizontal tangent line. And then we take a test point to the left of c, a test point to the right of c, evaluate our first derivative, and we find that we have negatives on both sides. So there's no transition from negative to positive, positive to negative. It's all negatives. So that means that the underlying function f of x is always decreasing on that interval. And also we can conclude that there is no local maximum or local minimum here, right? Remember, in order to see a local max or local min, we need to see this transition from negative to positive slopes. The first derivative needs to go from negatives to positives or from positives to negatives. But if there is no transition, they're both positives or they're both negatives, we will not see a local max or a local min. Okay, the other way that we can have a critical value at c is if f prime of c does not exist, right? All these cases up here were the cases where f prime of c equal to 0, therefore c qualified as a critical value given, well, we were given that c was a critical value, therefore f of c is defined. Okay, so f prime of c is undefined, but f of c is defined, means that c gets to be a critical value. So graph-wise, it could be that we have a sharp corner there, right? Places where we have a sharp corner, the function is defined there, but the derivative is not defined there. Or it could be somewhere where we end up having a vertical asymptote, right? It kind of, excuse me, not asymptote, but the graph goes vertical for a second, completely vertical, like in this example or this example. Okay. All right. So in this case, we have a value c. It's not defined there, so does not exist. And then we take test points to the left of c, to the right of c, and evaluate the derivative. So if the first derivative to some test point to the left of c results in a negative value, and then we take another test point to the right of c, and then we evaluate our first derivative there, and it turns out to be positive, then we do have a transition from negative to positive, so we have a local minimum at f of c. F of c is a local minimum. On the other hand, if we see that test points to the left, a test point to the left of c results in a first derivative that is positive, and then a test point to the right of c results in a first derivative that is negative, again we see a transition from positives to negatives, so f of c is a local maximum. And then just like before, in both of these cases, we find that when we take test points to the left and to the right of the c value, we do not see a transition. In this case, Test points to the left and to the right result in first derivatives that are positive in both cases. And in this situation, when we take test points from either side of C, we see that the first derivative is going to be negative every time. Okay, so in both of these cases, f of c is neither a local maximum nor a local minimum. Okay, so this kind of covers the cases we are going to run into. Okay, so given that f of x equals to 4x cubed minus 6x squared minus x plus 7, A, find the critical numbers of f, B, find the local maxima and minima of f, so local maximums, local minimums, and finally draw a sketch of our graph. Okay, so this is a nice classic example from this section. So this is what I want to do. This is kind of the order in which I want to tackle this. Number one, I'm going to find the derivative. Find f prime of x. Find the derivative. Number two, we want to find the partition values of this. Number two, we want to find partition values. Good. So that, remember, that's all x such that either f prime of x equals to 0 or f prime of x equals to does not exist. So find all those values. Number three, once you have those values, you compare it back to the domain of the original function f of x so that we can find the critical values. So we're going to have to come back over here and find the domain of the original function f of x. And 4, now we can compare those values that we found as partition values to our domain, and we can find the critical values. Once we find the critical values, we're going to create a sign chart. 5, create a sign chart, where we use our critical values or our partition values to separate our sign chart. And then we're going to use test points. For f prime of x. I want to know what's happening to the derivative. When is it positive? When is it negative? Once we have that, then we can use the test points to figure out 7. We can figure out when the function is, when f of x is increasing and when is it decreasing. Number 8, we can find our local extrema. Okay, so here's my little laundry list of all the things I want to accomplish to be able to answer this question right here. Okay, so let's begin with number 1. Let's find the derivative. Luckily, that's going to be pretty easy here. F of x equals to 4x cubed minus 6x squared minus x plus 7. So that means f prime of x is going to be equal to 12x squared minus 12x to the first power minus 1. Good. Okay, so now find all the partition values. Figure out all the values where our derivative is undefined or where equals to 0. Well, this is a polynomial, so it's not undefined anywhere. F prime of x equals to does not exist. This part will have no solutions, no values of x for this one. Okay, so now the other one is going to be, when does it equal to 0? All right, well, we set it equal to 0. 0 equals to 12x squared minus 12 minus 12x minus 1. And then we can use the quadratic formula. So this is the case where a equals to 12, b equals to negative 12, c equals to negative 1. And so we know that from the quadratic formula that x must be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. which means that x is equal to negative 12 plus or minus, well, you might actually, let's put it in different color. So I'll just put blanks there, and then it's going to be blank something squared minus 4 times blank all over 2 times blank. Okay, the role of b is being played by a negative 12, so that's going to be negative 12 there, negative 12 there. The role of a is being played by a positive 12. The role of c is being played by a negative 1. And then the role of a is being played by a positive 12. Okay, so I can simplify this a little bit and get that this is going to end up being positive 12 plus or minus, and this is going to be 144 minus, so plus 48. So square root of positive 144 plus 4 times 12 is going to be 48 all over 24. So this is going to be x equals to 12 plus or minus the square root of 192 all over 24. So 144 plus 48, confirm. Yep, and then I want the root of that to the 0.5 power. Gets me to that decimal. And so it's 13.8564. 13.8564. So let's say this means that x equals to 12 plus 13.8564 plus or minus all over 24. So one of those cases will be equal to 12 plus 13.8564 divided by 24, whereas the other case will be x equals to 12 minus 13.8564 divided by 24. So 12 plus 13.8564 divided by 24 is 1.0773 4. 0774. 1.0774 approximately. And in the other case, that 12 minus 13.8564, it's going to be that decimal divided by 24 will be 0.774 negative. Negative 0.0774. Okay, so we have our two partition points. So these are both partition points. .0774 and negative 0.0774. So here are two partition points. And now we come back and think about our original function and the domain of our original function. So this was step 1 here. We found the derivative. Step 2 was to find the partition point. So let's highlight it. All of this is 1. All of this work here is 2. That was a lot of work. So here they are, the partition points. That takes care of 2. 3 is to think about the domain of our function. 3, the domain of our function. Now, luckily, this is a polynomial. So f of x is a poly. So therefore, the domain is all real numbers. Domain is from negative infinity to positive infinity, all real numbers. Step 4 is to think about those critical numbers. 4, well, the domain is all real numbers, therefore both of these are in the domain. Therefore, those two numbers can now be upgraded to be critical numbers. Thus, x equal to 1.0744 and negative 0.0744 are both critical numbers. Okay, so we took care of 4. Number 5, now we create this sign chart. So number 5, we're going to think about a number line. And over here we have the value 1.0744. And then say over here we have negative 0.0744. This is the x-axis. So we're going to have to think of test points. We have 3 regions. How about if I choose negative 1 as a test point? How about if I choose 0 as a test point? And how about if I choose 2 as a test point? Right? These are nice whole numbers that are in each one of these regions so that I can figure out what's happening from negative infinity up to this number. And then also figure out what's happening from this number up to infinity, and then the middle one between these two numbers. Okay, so kind of off to the side then, we're going to have to evaluate our derivative. Now this was our derivative here, so we're going to have to evaluate our derivative at each one of these points. So now I'm going to take f prime of x, which was equal to 12x squared minus 12x minus 1, and I'm going to evaluate it at each one of those values. So I'll maybe create a little table over here. Prime of x. X. And so we have negative 1. So when I put negative 1 into here, I'll get 12 times negative 1 squared minus 12 times negative 1 minus 1. And remember, all I really care about is whether it's going to be positive or negative. So this is going to be positive 12 plus 12 minus 1. Definitely greater than 0, a positive answer. Okay, so coming back up here to my sign chart, I'm going to put on here that the first derivative, f prime of x, is going to be positive in this region here. Okay, so now coming back to my chart, then let's try 0. If I put in 0 into that first derivative, I'll get 12 times 0 squared minus 12 times 0 minus 1. 0 minus 0 minus 1, this is definitely going to be less than 0. I'm going to get a negative. So coming up to my sign chart here, the derivative is going to be negative in this region. The first derivative is going to be negative in that region. Good. And then finally, picking a test point over there, let's choose 2. So I'll end up with 12 times 2 squared minus 12 times 2 minus 1. So this will be 4 times 12 is going to be 48. Uh, 4 times 12 is going to be 48 minus 24 minus 1. It's definitely going to end up being positive. So up here, coming back up here to my sign chart, again, this is going to be positives. Let me zoom into this chart here. Okay, so we took, we created a sign chart. We figure out when that first derivative is positive, when it's negative, when it's positive. We took some test points. Let me make some space here. This is too big. In fact, I'm going to go the other way around. So I'm going to put the test point was over here at negative 1. There was a test point at 0, and there was a test point at 2. Good. All right, so now on this interval from negative infinity, let's put it in green, on the interval from negative infinity up through negative 0.0744, because the first derivative is positive, it means that the original function f of x is increasing on that interval. Okay. Here, the first derivative is negative, which means that on this interval, on the interval from negative 0.0744 up through positive 1.0744, on this interval, f of x is decreasing. F of x is decreasing. Good. And finally, on this interval, from 1.0744 up through positive infinity, in this interval, the underlying function f of x is increasing, right? Because the first derivative was positive in that zone. Okay, finally, at these points, we see that there is a change in the sign of the first derivative. It went from positives to negatives, so that indicates that at this point, we have a local max. Local max. The slopes are positives, we hit 0, and then negative. So that creates a local max at this point. And then at this point, we see that we're going from tangent lines that have negative slopes to tangent lines that have positive slopes. So at this point, we see that we have a local min. Okay, so let's see if we've answered everything. Okay, so we were asked to find the critical numbers of f, to find the local maximum and minimum of f, and then to do a rough sketch of f. Okay, so we found the derivative, right here. We found the derivative of our function. That's step 1 in this process, took care of that. Then we found the partition values by setting it equal to 0 and solving. We used the quadratic formula, so we found these 2 points right there. For this function, because it's a polynomial, there won't be a case where we have an undefined, but look out for situations where you might be dividing. Remember that the denominator of a fraction can't be equal to 0. Or if you're taking the square root, the even root of a function, make sure that you're not accidentally taking the even root of a negative number. So those are things to look out for. Also remember that log functions are defined for an argument that's greater than 0, strictly greater than 0. So you have to be careful to figure out which values result in a derivative that is undefined. But in this case, we didn't have any. So we took care of this part here. Next, we thought about the domain. Here it is. So the domain, because it's a polynomial, the domain of the underlying function is a polynomial. It's defined on all real numbers. These points are in that domain. Therefore, they can be upgraded from being partition points to now being critical numbers. And that leads to the answer to part A. Part A answer is right here. These are the critical numbers. Good. Okay, local extrema. So now we keep going. We use our partition values, these two right here, to separate our number line x. And then so that creates 3 zones. We have to take test points, nice convenient values from each zone. So maybe -1, 0, +2, just arbitrarily chosen. And then we test them. We evaluate our derivative function at each of those points. And our goal is just to establish whether the derivative is going to be positive or negative in that zone. When we tried -1, we saw that it was definitely positive, right? We got like 23. So that's why we can conclude that all of these are positive. When we tested 0, we can conclude that we got a negative. And so the first derivative is negative in that zone. And then when we tried 2, we see that it's positive in that zone. Okay, when we have that, that answers, that's part of finding the sign chart or creating the sign chart and finding test points. We did this, we did that. And then increasing or decreasing. Well, the function the original underlying function is going to be increasing whenever the derivative is positive. So it's increasing in this zone, and decreasing whenever the first derivative is negative. So it's going to be decreasing in this zone and increasing in this zone. And then finally, to answer part B, we need to see that there is a sign change in the first derivative. Here it goes from positives to negatives. That's how I know there's a local maximum here. And then it changes from negative to positive. That's how I know there's a local minimum there. So that's going to be our answer to part B. So I'll put part B over here. There is a local max at x equals to negative 0.0744, and there is a local min at x equals to positive 1.0744. Okay, so we answered A and B. Part B, sketch the graph. Okay, so we can do a rough estimate of what this graph looks like. And to really get a really good sense, you need some test points here. So create a table of values. You can create a table of values, evaluate our function at a few key, somewhat easy points. But don't be afraid to use technology at this point. It's not wrong to use technology. You just have to justify and back up your work. So when the test comes around, I'm not going to just say, graph it, and then that's the answer. I need you to confirm for me what the critical numbers are and how we know that there is a local max or a local min by creating a sign chart, stuff like that. So make sure that you were able to follow this process in order to be able to confirm where these key items are. Okay, so let's just use technology to graph it, and then we'll come back and confirm that these results make sense, that this sign chart makes sense for the results that we get. So I'm just going to go to Desmos. Okay, so I came over to Desmos. I typed in our equation, 4x cubed minus 6x squared minus x plus 7. And here's the graph that we got. Okay, so confirming that we have a local maximum here at this point. Nice thing about Desmos, you can just click onto it. So we get that at x equals to negative 0.77, we have a local maximum there. And then over here at x equals to positive 1.077, we have a local minimum. So we have that, we have a local maximum here. And this kind of translates down to negative 0.774. X equals to 0.77. We have a local max. Local max. We have a local min here. Local min at, and then this comes down here, at x equals to 1.0774. And we can confirm that the function is increasing from negative infinity up to this point of the negative 0.077. Oh, this is an extra 0 in here. Negative 0.774. So up to there, the function is increasing. So f of x is increasing on this part. And then the function is decreasing. F of x is decreasing up to there, from this point to this point. From this point to this point, the function is decreasing. And then from this point to this point, the function f of x is again increasing. From this point to that point. Okay, so f of x is increasing, f of x is decreasing, and f of x is increasing, which means that f prime of x is greater than 0 here, f prime of x is less than 0 here, and f prime of x is greater than 0 here, right? If you think about all the tangent lines, a tangent line over here, a tangent line over here, the slopes are all going to be positive here, so the first derivatives are all going to be positive in this zone. The first derivatives are all going to have negative slopes over here. The first derivatives are all negatives. The tangent lines are going to have negative slopes in this zone. And in this zone over here, the first derivatives are all going to be positives. Okay, so what if you didn't have decimals? How would you get this picture? Well, a lot of work, right? So aside from knowing this information down here, it would also be nice to come up with some extra kind of convenient points, so that if I knew that there was a local maximum there, and maybe I also knew where the y-intercept was, maybe I knew a couple of other interesting points around there, I knew this was a local min, maybe I knew another point over here. Okay, let me make them in purple so they stand out a little more. See, this point, this point, this point, this point, this point, and maybe some other point over here. And, you know, if you can get it, maybe this point over here. So if I knew this point, maybe somewhere around there, somewhere around there, somewhere around there, and we know that there's a local maximum there and a local minimum here, we can start to kind of sketch together where our function values are. To get these purple values, well, we have to evaluate our original function. Our original function was equal to 4x cubed minus 6x squared minus x plus 7. So what we could do is just evaluate this function at various points to find a few other interesting points. That, coupled with our knowledge of when the function is increasing, when there's a local maximum, when there's a local minimum, can help us put together a good sketch. So in order to get some extra values here, I encourage you to use the table value of your function. So we're going to put this into our calculator, and then we're going to choose test values so that we can get these ordered pairs, right? Just kind of randomly select some good ones that can kind of begin to give us this picture. Okay, so to do that, let's go over our calculator. Okay, once your calculator is turned on, we're going to go over to where it says y equals, clear, put in your equation. So 4 and then x to the power of 3, and then minus 6x to the power of 2, and then minus x plus 7. Now, the software in my calculator is a little advanced that it lets you do this exponent and kind of shows you that it's in the exponent. A lot of calculators are just going to have this caret symbol, and then that little caret symbol appears there rather than it jumping. So be careful with your own calculator of what it does. And if it does do that little caret symbol, maybe wrap the x to the power of in parentheses so that there isn't a mistake about what you're typing in. Okay, so we type in our equation. Next, we're going to go over to where it says table set. So second table set. Make sure that this is under, independent is under ask, and dependent is under auto. If it's not like that, use your arrows to come down and select it to be like that. Okay. Next, you're going to hit table. So hit second table, and then whatever is already there, delete, 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 delete. Okay, what this is a place where you can have your function evaluated for any input value without really, doing the calculations for it. So for example, a really easy one would be if I replace all those x values, if I put a 0 there, 0 there, 0 there, then it's just going to be a 7, right? So let's confirm that that's what we get. Put a 0 here, enter, and see we get a 7. Make that a little bit bigger. See, we get a 7. On the other hand, if I plug in a 1, that should be another easy one. 1 there, 1 there, 1 there. I should get 4 minus 6, that's negative 2, minus 1, that's negative 3, plus 7, that should be positive 4. Okay. And there, it calculates it and gives me a 4. So this is a really great place for me to just find a bunch of values to my function, and again, hopefully get enough points so that I can find these purple values, purple dots, give or take, so that I can get a rough idea of what the graph looks like. Okay, so looking at my domain here, let's pick out some points. Looks like maybe -1 would be a good one. I can confirm that it's down here somewhere, negative. I don't know, how about -0.8 would be a good one? About -0.5 would be a good one. About, well, something really close to that. How about -0.1? And then, of course, we know that -0.0774 is an important value. Let's let x equal to 0 so I can figure out that point right there. Something in the middle here between these. How about that +0.4? How about +0.8? Just randomly picking a few points in this green zone so I can have a sense of what the function is doing there. I also know that +1.0774 is another important value. And finally, something bigger than that, like maybe 1.5 or maybe even a 2. Confirm where that's going. Okay, so if I was doing this all by hand, this would be a lot of work to try and figure out all those things. Luckily, we can use our technology and easily fill out this table. Okay, so let's use our calculator. So filling out that table, you start with -1, gives me that guy. Looks like it's -2. Then -0.8 leads to that. Then -0.5 leads to that. And then -0.1 leads to that. And then -0.0774 approximately leads to that. And then 0 leads to 7. And 0.4. And then 0.8. And then 1.0774. And then 1.5. And finally 2. Okay, so I hope you realize that a lot of these were chosen just kind of arbitrarily, just some values in each one of these zones, again, so that I can have some sense of what my function is doing for all those values. So I can fill out my table from here. Okay, so we can create our table, and then hopefully from that table, again, just get like a rough sense of what the sketch is doing. Of course, as long as we have technology, why not use technology to graph it? So let's go back to our calculator and graph this equation. So go back to your calculator. You go to y equals, this is where we typed in our equation. Make sure that this equal sign is dark. If it's, see, like this, it's dark. This means it's active, it's going to graph it. If it's not dark, like maybe like this, hit enter, move down, see how it's no longer dark, it won't graph it. All right, highlight it, hit enter if it's not already dark, and now we're ready to graph it. Let's go over to where it says stat plot. Well, actually, you can just tell from here. See how plot 1, plot 2, and plot 3 are not dark? That means they're deactivated. If they were active, they would look like this. So hit enter here. See how plot 2 has this dark box like that? That means it's active. We don't want any of these things to be active. So come up here, highlight them if they're dark, hit enter, and then move away from them. And this is what you want to see. Plot 1, plot 2, and plot 3, and none of them have that dark box. None of them are active. Good. Okay, so now we want to graph it. So next let's go to window, and we already have a pretty good sense of the dimensions that we want to graph based on our table. Right, so it looks like -1 to 2 are good choices for x minimums. -1 to a maximum of 2. And let's go by scales of 0.5. And then the y's, again, looking at our table, looks like maybe -2 all the way up to a little bit past 7. How about 8? So from -2 to 8, -2 to +8 seems to be a good choice. Again, let's go by multiples of 1 this time. Enter. And now hit graph. And there's our graph. Okay.